Welcome to Brain Vision.
Hi, the given problem is based upon Stephen's law, according to which if we are having an object of surface area A whose absolute temperature is T, then the heat radiation emitted by its surface per unit area per unit time are given as E is equal to sigma into T raised to the power 4, where sigma is Stephen's constant whose standard value is 5.67 into 10 raised to the power minus 8 watt per meter square per Kelvin to the power 4. And this is when this object is in vacuum, means if we ignore the temperature of the surrounding. But in case of the temperature of surrounding also given to us, for the surrounding temperature also given, if it is T naught, then this law takes a form, the energy emitted per unit area per unit time will be given as sigma into T raised to the power 4 minus T naught raised to the power 4. And this law is applicable for a perfectly black body. But in case the body is not perfectly black, as here in the given problem, it is tungsten, which is not perfectly black body, then we should know its emissivity. And in that case, now the final form of Stephen's law becomes emissivity epsilon times sigma T4 minus T naught 4. And here this is the energy per unit area per unit time. So if we look only for energy per unit time, it will become power radiated by the surface. So it will become power radiated by the surface per unit area is equal to sigma is equal to epsilon into sigma T4 minus T naught 4. Hence, finally, the expression for the power which we have to find in this given problem comes out to be epsilon into sigma into A, the surface area of the tungsten sphere, into T4 minus T naught 4. So this should be the power input required to maintain the sphere at the temperature of 3000 Kelvin, where the temperature of surrounding walls are given as, it is given as 290 Kelvin. And obviously when we will have the fourth power of these temperatures, this T naught power 4 will become negligibly small as compared with T raised to the power 4. So we can use P is equal to epsilon into sigma into A into T raised to the power 4. For area of the sphere, it becomes 4 pi r square into T raised to the power 4. So finally, plugging in all known values here, for emissivity, this is 0.35. For sigma, this is 5.67 into 10 raised to the power minus 8, 4 into 3.14. Radius of this sphere has been given as 1.5 centimeters, so it becomes 1.5 into 10 raised to the power minus 2 to the whole square, and finally 3000 to the power 4. So it becomes 4.54 into 10 raised to the power 3 watt. So this should be the power supplied to this tungsten sphere in order to maintain its temperature at 3000 Kelvin. So this is the answer for this given problem. Thank you.